the chem activity 4, we'll continue our exploration of the connection between hybridization, arrangement of electron pairs or electron pair geometry, and molecular geometry. We will turn our focus in this chem activity to atoms other than carbon, and thereby we will need to introduce the concept of steric number. In this first slide, we see a representation of methane, ammonia, and water. Now you may recall that in the case of methane, it has 4 sigma bonds, and we connected the idea of 4 sigma bonds to an sp3 hybridization and to an electronic and molecular geometry of tetrahedral. The carbon has 4 regions of electron density around it. We will extend this analysis to nitrogen and oxygen and other atoms. But in this case, we will not only look at the number of sigma bonds, but we'll also consider the lone pairs. So by summing the number of sigma bonds and the lone pairs, we come up with what's called the steric number. So the carbon in methane has a steric number equal to 4, as it has 4 sigma bonds. But the nitrogen in ammonia also has a steric number of 4, because it has 3 sigma bonds and 1 lone pair of electrons. The oxygen in water has 2 sigma bonds and 2 lone pairs of electrons. Therefore, it also has a steric number equal to 4. So steric number indicates the total number of electron pairs, whether they be bonding pairs or lone pairs, around that central atom. Now this is helpful because it allows us to make predictions about the geometry about that central atom. And this is based on VSEPR theory. So VSEPR theory, or valence shell electron pair repulsion, posits that electron pairs arrange themselves around a central atom to minimize the electron pair repulsion. So based on this theory, we would expect that all 3 of these molecules would have the same electronic geometry or electron pair geometry. To see how this might work in a simulation, let's take a look at one of the PhET simulations that relates to electronic and molecular geometries. The idea here is we have 2 atoms around a central atom, and VSEPR theory posits that it's the electron pairs that repel one another and will arrange themselves so as to minimize the repulsion. Now we can say that the molecular and electronic geometries here are both linear, and of course we'd expect the bond angle to be 180 degrees. Now if I pull on one of the atoms and try to bring the pair of electrons between that atom and the central atom closer to the other pair of electrons, you can see that initially there's a distortion, a bond distortion, but afterwards again the linear geometry is adopted. This minimizes the repulsion between this electron pair and this electron pair. If we introduce another bonding pair of electrons, you can see the trigonal planar orientation. Note that of course all the atoms and bonds are along the same plane, and we can see that the electron pairs here, and electron pair here would arrange themselves so as to minimize the repulsion between those pairs. We can also add another bonding pair, and so you can see that we have the tetrahedral once again, and the bond angle is, as we'd expect, 109.5, and no matter if I try to distort the bond angles, the tetrahedral geometry is once again achieved. In terms of connecting methane to ammonia, if I remove one of the bonding pairs and replace it with a lone pair, this is a situation that's similar to ammonia, where I do have 4 regions of electron density, I have 3 bonding pairs, and I have 1 lone pair. And collectively, they will adopt an electronic geometry tetrahedral. The molecular geometry, though, is referred to as trigonal pyramidal. And to get a sense of how this works, I am going to take away the lone pairs. And essentially, we just look at how these 4 atoms are arranged relative to one another. And hopefully you see that it looks like a triangular pyramid. So this would be the molecular geometry for the nitrogen in a molecule like ammonia, or of course our amine functional group. So now if we turn our attention to a molecule that's like water, so I'm going to add my lone pair back, I'm going to take away a bonding pair, and I'll add another lone pair. So this would be like water where the central atom here would be the oxygen, and then we have two hydrogens. Again, the electronic geometry is tetrahedral, as I have a steric number equal to 4, or 4 regions of electron density that arrange themselves so as to minimize the repulsion. But the reason why we refer to this geometry or molecular geometry as bent is if I take the lone pairs away, you can see that the 3 atoms here relative to one another adopt a bent shape. So let's go back to the slide and summarize some of these ideas. So here we have representations of methane, ammonia, and water. In the middle column, I have a representation of the arrangement of electron pairs, or the electronic geometry, and in all 3 of these cases, the electronic geometry would be tetrahedral. We would predict that because the carbon, nitrogen, and oxygen all have steric numbers equal to 4. The molecular geometry is a little bit different in the sense that, of course, because carbon doesn't have any lone pairs of electrons, its electronic equals the molecular geometry, and of course the molecular geometry here would be tetrahedral. The molecular geometry, however, for ammonia would be trigonal pyramidal. So that lone pair of electrons does influence the overall geometry, but it's not actually seen, if you will, in the molecular geometry. And finally, the water would have a bent molecular geometry. We should talk a little bit about bond angles. And so for methane, of course, we would expect the bond angle, that is the hydrogen-carbon-hydrogen bond angle, to be what's typical for a tetrahedral, and that's 109.5. In the case of the hydrogen-nitrogen-hydrogen bond angle in ammonia, the actual bond angle is about 107.8. The actual bond angle for the hydrogen-oxygen-hydrogen bonds in water is 104.5. So you can see these bond angles are less. We postulate that this happens because the electron pairs take up more space than a bonding pair, and therefore they have more effective repulsion than the bonding pairs. So in a sense, they push down on the bonding pairs. We don't ask that you know these specific numbers, but we do ask you to realize that in the case of having lone pairs of electrons, the bond angles will be less than what you would have typically expected. Here I choose methane again, and of course it's going to have the expected bond angle for a tetrahedral. Bond angles between the hydrogen, carbon, hydrogen of all 109.5. If I now choose the ammonia with its lone pair of electrons, the bond angles here are 107.5. And once again, it's this idea that lone pairs spread themselves out more, so they repel more with these bonding pairs, and essentially push down on all the bonding pairs. You need to know that this angle is less than 109.5. And if we turn to water, you can see that the bond angle here is expected to be about 104.5. I simply need you to know that it's going to be less than 109.5, and perhaps even less than what you'd expect in terms of having a single lone pair of electrons. That is, there's more repulsion when you have 2 lone pairs of electrons. In this next slide, we summarize these ideas in this table. So of course, all 3 of these molecules have a steric number equal to 4. Now, I want you to make the connection that with a steric number equal to 4, just like with methane, the other 2 molecules will also have a hybridization of sp3. So we could go through the atomic orbital diagrams and prove and justify why this might be the case. But I'd rather, at this stage, you just make the connection that any atom that has a steric number 4, we would expect the hybridization to be sp3. And correspondingly, the electronic geometry, or the arrangement of electron pairs, would be tetrahedral. However, if we have some lone pairs of electrons, then the molecular geometry will not equal the electronic geometry. And indeed, this is true for the ammonia and for water. Yes, you do need to know these names and also spelling counts. So let's look at the example now of what happens when you have a steric number equal to 3. So these 3 molecules all have steric numbers equal to 3, and you can see at the top here I have a title. Steric number of 3 is associated with sp2 hybridization. We knew that carbon making 3 sigma bonds had an sp2 hybridization. Well, a steric number of 3 is also associated with an sp2 hybridization. So we're looking at boron, nitrogen, and a carbon also. And all 3 of these have steric number equal to 3. In this case, if there are no lone pairs of electrons, as in the case of boron trichloride, then the electron pair geometry will equal the molecular geometry. So of course the electronic geometry in all these cases is trigonal planar, And in the case of boron trichloride, the molecular geometry equals trigonal planar. In the case of this partial molecule here that involves the nitrogen with a double bond, that geometry here would be bent. Now again, we're only focusing on the arrangement of the three atoms, or the two atoms around a central atom, and ignoring the lone pairs, if you will. So that geometry would be bent. And then lastly, we'd say that the carbon in this molecule formaldehyde, that carbon here has a molecular geometry equal to trigonal planar, as there are no lone pairs of electrons around the central atom. In terms of bond angles, we'd expect 120, as there's no additional repulsion by a lone pair of electrons. We'd expect actually the bond angle here, the carbon-nitrogen-carbon bond angle, to be less than 120, because again, there's enhanced repulsion by the lone pair of electrons. But in this next example, again, the bond angle would equal that would be typical for a trigonal planar geometry. You may be wondering about the oxygen in formaldehyde, so I'm just going to circle it here, this guy right here. So that oxygen also has a steric number equal to 3, because it's got one sigma bond and two lone pairs of electrons. So its electronic geometry would also be trigonal planar. We don't talk about, however, a molecular geometry for a terminal atom like that. So we would need one additional atom attached to the oxygen to start to talk about bond angles. But we indeed can talk about an electronic geometry. Note that having a pi bond doesn't influence the geometry. So again, steric number is just the sum of sigma bonds plus lone pairs of electrons. Back to a table to summarize this information. All three central atoms in this case have a steric number equal to 3. All three would have a hybridization of sp2. All three would have trigonal planar electronic geometry. The middle molecule has one lone pair of electrons, so 0, 1, and 0. Anytime that there's no lone pairs of electrons, the molecular geometry will equal the electronic geometry. And of course, the molecular geometry for the nitrogen in the central atom is bent. And the last example here, we have a steric number equal to 2. Again, we're focusing on the number of sigma bonds plus any lone pairs of electrons. Neither of these molecules have lone pairs of electrons about the central atom. Therefore, both the electronic and molecular geometries will be equal. And in this case, these geometries are linear. And of course, the bond angle here would be 180 degrees. This chart also summarizes some of these ideas. Steric number equal to 2, hybridization equal to sp, arrangement linear, lone pairs of electrons 0, therefore the molecular geometry equals the electronic geometry. In this next chart, we summarize these ideas yet again. So it's this idea of, well, what are the steps in determining, for instance, the molecular geometry? So of course, the first thing that you need to do is be sure that you know what the steric number is about that central atom. So you simply count the number of sigma bonds plus lone pairs of electrons. If it's a steric number equal to 4, well then we'd expect electronic geometry to be tetrahedral, and of course the hybridization is sp3. Steric number equal to 3, trigonal planar, sp2, and of course steric number equal to 2, linear, sp. In terms of thinking about molecular geometry, we actually ignore the lone pairs to see how the atoms are arranged. But we're not really ignoring the lone pairs. We're considering that they're there because that allows us to come up with an actual description or terminology for the molecular geometry. So no lone pairs, tetrahedral. One lone pair, based on steric number 4, leads to trigonal pyramidal, and two lone pairs, of course, bent. But you may have noticed actually there are two ways of having a bent structure. If we have a steric number equal to 3 and one lone pair, we also have a bent structure. You might appreciate, however, that the bond angles are different. So in the case of steric number equal to 4, we would have a bond angle of less than 109.5. In the case of water, remember it's around 104.5. Whereas in the case of steric number equal to 3, the bond angle is on the order of 120 degrees. If there are no lone pairs, of course, then the electronic equals the molecular geometry. Finally, in the case of linear, and actually you can't have lone pairs of electrons in terms of linear because then you can't describe the geometry. You need to have atoms on either side about that central atom. So linear, sp hybridized, and of course electronic equals the molecular geometry.